In this unit, we're going to be looking at thermodynamics. We have 4 lessons we are going to cover. The first lesson, we'll look at heat versus temperature. The second one, we'll look at thermal expansion. The third lesson, we'll deal with sensible and latent heat. And the fourth lesson, we'll look briefly at thermal equilibrium and a few review questions. Lesson 1, temperature versus heat. What is the difference between temperature and heat? We often think of the two the same, and it's just what we've been conditioned to. We talk about, well, something is hot, and we think of hotness being associated with heat. We think of a fire giving off a lot of heat because it's hot. But ice also has heat, which sounds strange to us, but ice does. It has energy, so it has heat. So the difference between temperature and heat is temperature is how hot or how cold an object is. So an object may have a temperature of 0 degrees. That doesn't tell me anything really about how much heat it has. I'm going to use that information to calculate how much heat it has. The amount of heat the object has is a measure of its thermal energy. Now, I actually really like this section because I'm a chemist, and from a chemistry perspective, I've looked at this a lot. I've had to take four courses in physical chemistry, which looks at thermodynamics and the transfer of energy. I'll confess, was not our favorite subject at the time. And I promise you, you won't get near as complicated as we used to. So I think you'll actually find this quite manageable. But it's really interesting to think about how is energy transferred and what that means. So when we say temperature is a measure of how hot or how cold an object is, and heat is a measure of the thermal energy, one of the ways that we can think about heat is related to how fast the molecules in that object are able to move. So if they're moving very rapidly, they have a lot of energy. And what I like to think of it as is I often like to think of it of heat and temperature, how the two are related, as if you had a room full of people. Okay, so let's think of a gymnasium in an elementary school. Most of you can go back and think about days when you were in elementary school and you're in a gym. You've got a whole pile of kids. At first, when you come in, you come out of that change room, it's chilly. Nobody's running around yet. You can think of that as low energy. Low energy, cool temperature. Now you get all those kids running around, bumping into each other, the room heats up. We have a lot of energy in the room, and therefore the temperature increases. Now, I know that's a very simple explanation, but that's something that I often use to help give us a visual, because heat is related to the thermal energy of the object, which is related to how fast the molecules in that object are moving. The faster they're moving and bumping into each other, the more likely they are to be at a high temperature. I often will compare it to friction. Friction rubs against things, and when we have friction in gears or when we have friction in machinery, it results in heat. And I often think of molecules bumping into each other as creating friction and resulting in heat. So that's just some little story tools I use to help me better understand the difference between heat and temperature. Now on this slide, I have a great image which helps us understand the difference between heat and temperature. So if you look at these two beakers, we have two beakers that are both at 100 degrees Celsius, okay? So the temperature is the same. But if you stop and think about, is the heat the same? Well, let's think about how much energy it would take to heat the water or whatever liquid is in these beakers up to that 100 degrees Celsius. So the first beaker, where we have a smaller quantity, we know that this is going to take less time. And if it takes less time on the stove, it's going to require less energy. Okay? So if it has less energy, that means we have, the big word is, it has less heat as compared to this one, which has more heat. Because there's more stuff to heat up. There are more particles that we need to transfer energy to. If you think about it as far as when it's on the stove, it requires more time to heat. And it's gonna, the more time it takes for something to heat up, it requires more energy. I'm still getting used to talking and writing at the same time, so you'll have to bear with me, okay? So I think that makes the difference between heat and temperature fairly straightforward. If you have questions about it, please let me know. The other thing we need to look at right at the beginning is we need to know the types of heat transfer and what way heat is transferred. Now, because heat is energy, energy always moves downhill. If you need proof, think about how you feel after you've had a cup of coffee. Had that cup of coffee, for most of us, it gives us the energy boost. Our energy doesn't continue to increase, it always goes downhill. It's like that for all energy that we encounter in life, whether it's energy from our food, which goes downhill, or if it's energy from temperature that goes downhill. The heat from my house is lost to the outside. The cold isn't coming in, but the heat instead goes out because the cold outside air has less energy than the warm inside air. So heat's always going to be transferred from the hot substance to the cold substance. It will never transfer the other way around. Now, some of you may say, but how do heat pumps work to heat in the wintertime? Let's wait until we get to our fluid section. Heat pumps work based on compressing gases. So knowing what happens when gases compress is going to explain why we can extract heat from the cold outside. But just like I said before in the last slide, even ice at 0 degrees, so we think of the temperature as being low, at 0 degrees, it still has heat. It just has less heat than if it was at 25 degrees. Now, in a closed system, energy is conserved. Same thing you had when you did your unit on simple machines, energy is always going to be conserved. So the amount of heat lost from inside of my house to the outside is also gained. Okay, so energy gets conserved there. It's just that my house being small, I feel the difference much more. And because the outside air is so large, it makes a minimal difference on the environment. Now, there are 4 types of heat transfer. We're going to look at them on the other side. We're going to see radiation, convection, and conduction, or 3 types of heat transfer: radiation, convection, and conduction. So we're going to look at the definitions on the next slide, and then I'm going to pop back to this image. So first of all, for heat transfer, we have conduction. So conduction is when heat is transferred from molecule to molecule through a substance. Okay, so heat traveling through walls or heat traveling through my windows. Right now, I have a problem with my windows at home. The seals are gone on those windows. So we're working at replacing a lot of them. Because the seals are gone, it makes conduction happen very easily because there's moisture in between some of the panes. So that's heat traveling from the molecules of the air in my house through the glass molecules of the window, the moisture that's in that little vacuum that's causing me to lose more heat than usual through the outside pane, and then to the molecules of air on the other side. So that's an example of conduction. We're going to look at that on the stove example in a minute. So conduction is heat loss through your walls or through your windows. One of the big things to watch for, especially if you're somebody that's maybe thinking about buying a house or has bought a house in the near future, is thinking about a lot of heat is lost through our attics. And one of the reasons why we lose a lot of heat through attics is because of convection and conduction in a house. So convection is when heat is transferred through a fluid, such as air or water, by the movement of molecules. So we're just thinking about air blowing around. Think about lots of you, I'm sure, have seen convection ovens. They've got the big fan in the back to move the air. So convection results because of movement of molecules. It's not transferring from one substance to the other. Instead, the molecules are just floating around. So molecules with higher energy are moving in some places, and the molecules with lower energy are in others. Now, we know heat rises. It has more energy, so it's going to rise. So if we think about in this house scenario, the heat rises, and as the heat rises, it's going to heat my ceiling more, which if my ceiling isn't well insulated is going to result in more heat in my attic. So I have conduction happening through the walls to the attic. And then eventually that heat that I've had result in the attic is going to conduct. So we have convection happening in the attic, and it's going to conduct through the outside. Now, one of the things that we do in construction is we'll put vents on each end of houses. It helps to control moisture, but it also helps keep that attic air cool. But it's also the reason why we need to have lots of insulation, because cool air that's blowing through our attic. So take a look at your house and see on the two gable ends, so that's the two ends that have your triangle shape, most likely be your two ends with your triangle shape is where you'll see it. You may see somewheres up there, you may see a little vent. Okay, and that vent allows air to pass through your attic. That's a good thing to have. You want to have that, or else you can have mold buildup and whatnot. But if that vent's there, that means you've got cold air blowing through the attic. So if warm air is coming up through your roof and that cold air is dropping, it's cooling off your ceilings. If it's cooling off your ceiling, we're going to find it cools off the entire house. We'll come back to that when we look at some thermal equilibrium examples. So if you're thinking about buying a house, one of the things you should always watch for is where can you save on energy, because this makes a big difference in your heat bills. And one of the things to watch is actually one of the cheapest places to fix. Windows are expensive to do. I've got a room with four windows and a door, and the bill for the windows and the door prior to installation was over $8,000. So windows are expensive, but adding extra insulation to an attic, if your attic needs it, which our attic needed it when we purchased, is one way to reduce the conduction of heat through the attic to the outside. Just because insulation doesn't, just like insulators don't conduct electricity well, insulation in a house does not conduct heat well. And we'll look at the reason for that when we get to talking about sensible heat. So we've got conduction, we've got convection, we've got a long example. The other one type of heat we have is radiation. And given that we're just about the 1st of April tomorrow, one thing I noticed this time of year is the strength of the sun, the strength of the radiation of the sun coming through my windows, resulting in heat transfer. Outside, it's still cold, but when that sun shines through, it helps to warm the house. So that's an example of heat transferred by electromagnetic waves. That's also the premise that your microwave works on. I'm not going to go down the microwave bunny trail because I get way too excited when you get thinking about how microwaves work. I spent a couple years doing research with that, and the effect of radiant heat is really, really, really interesting because it's through electromagnetic waves. Electromagnetic waves could also be like X-ray, radio waves, gamma rays, those kinds of things. There's all kind of speculation about the types of radiant heat and what radiant heat is safe and what is not. We've actually gotten pretty good at designing windows to help block radiant heat, because radiant heat, too much heat in the summertime makes the house too warm. And unfortunately, it does mean in the wintertime, maybe you're not gaining as much of that sun, but the sun doesn't have the same strength that time of year. So 3 types of heat transfer: conduction, convection, radiation. I've given you some personal examples of it. I will be asking you, when you get to your test, you can write this down so you have a few days to think about it. When you get to your test, I am going to ask you to give me some examples that are different than what I've given you in this lesson. So spend some time looking around you and see, where do you see examples of conduction, convection, and radiation? Now, if I just quickly go back to the last image, when we have a pot over a fire, we have radiant heat from the fire. Actually, this is not the best example of radiant heat, but it works for our purposes because the pot and the fire are not in contact. Convection is the fluid moving around in the pot. So we've got hot water on the bottom. The hot water naturally is going to want to go up towards the top. The cool water is going to fall. So that's going to create a cyclical pattern. And then we have conduction through the handle. Now, if you were in the wind turbine class, we had a really interesting example of convection happening in our class one day. When we were doing some velocity questions, shooting some Nerf gun bullets, and they were dropping very quickly the closer we got to the door. We could tell there was a downdraft by a cold door. Now, there's two things that could have been causing it. It could have been the ventilation system, but if we just think about heat rising and cold air dropping, that cold door would create, just the fact that it's cooler than the rest of the room would have created a little bit of a natural downdraft current. So there's another example of convection. So convection, conduction, and radiation. Now, what units do we measure heat in? Heat is energy. So if you remember from our previous units, we measure energy in joules, okay? So energy is measured in joules. We'll often see ratings for watts on equipment. If you have watts, that's a matter of power. That's going to be energy per second, okay? So a watt is equal to energy per second, or you could think of that as equal to heat over time. We're not going to use so much watts in this section, but just in case you're wondering, well, why is my hot water heater rated in watts as opposed to joules? One is power, the other one's the amount of work. So heat's really an amount of work when we think of it as being energy. So it's measured in joules or kilojoules. That's the metric unit. We're going to work mostly with the metric unit. You won't see very many questions with BTUs. To the HVAC crew, I apologize. I know you use BTUs all the time, but for now, you're going to have to think with me in joules. We'll look up the conversion down there in just a minute with kilojoules and BTUs. So what is a joule? A joule of heat is the amount of heat needed to change the temperature of 1 gram of water 1 degree Celsius. So that's how it was defined. Sometimes we measure heat in calories or kilocalories, and we think of that, I think of that more when I think of food. On all our food packaging, we see calories and kilocalories. Body temperature, we'll often think about our temperature, but then we'll often think about how many calories does a person need to have to sustain themselves. So you can think of that as the other unit of energy. That is also a metric unit. But again, we will work pretty well exclusively with joules. I say there are multiple units because you should be aware and watch for that. Your charts will give you multiple units. You're going to need to select the correct one for the final answer that you want to get. Now, in terms of imperial units, for imperial units, there's the British thermal unit, and that's equal to the amount of heat needed to change the temperature of 1 pound of water 1 degree Fahrenheit. So we have the other temperature scale, and then our weight, instead of being grams, we're looking at pounds. Now, something interesting to think about, there is a kilojoule of energy is very close to a BTU of energy. So 1 kilojoule is equal to 0.948 BTUs. So for those of you that are used to working in BTUs, it's almost 1-to-1. So for the purposes of estimating, if you see an answer in kilojoules and you're just looking for a rough estimate, you could assume kilojoules equal to BTUs. Of course, if you're needing more precise calculations, you would need to look up the conversion. Now the temperature scales. There are two temperature scales. I shouldn't say 2 temperature scales. I guess there's really 4 temperature scales. There's 2 for metric and 2 for imperial. So the standard temperature scale is this Celsius or centigrade temperature scale. in which water freezes at 0 degrees. So that's the metric system that most of us are familiar with. Some of you, especially if you're talking to your parents, they may be more familiar with Fahrenheit, where water freezes at 32 degrees Fahrenheit. I know if I'm talking to my grandmother will always give me temperature in Fahrenheit as opposed to Celsius. The absolute temperature scale is a temperature scale that's based on, so the 0 point of that temperature scale is when all motion of molecules stops. There are 2 scales for that as well. There are kelvins and there are rankins. We will use kelvins occasionally. We won't use rankins very much, just because in the context of physics, rankins are used quite rarely. We won't have to use the absolute temperature scale in this unit, but I will have you learn how to convert with it. The reason we won't need to use it in this unit and we still learn it is because in the next unit, when we look at fluids, we will need to know absolute temperatures. So you're going to want to keep that in mind now, and we'll briefly review it when we get there. You'll notice kelvins is not degrees kelvins. It's just one of those little things to notice. We have degrees Celsius, degrees Fahrenheit, but kelvins is just kelvins. At 0 kelvins, we call it the absolute zero temperature, and that is where all molecular motion stops. Now, for the Kelvin scale, water freezes at 273.15 kelvins. Water boils at 373.15 kelvins. So those will be 2 marks that we'll look at. This is the one that's going to be the most helpful for us. And we'll look at what our formula is for figuring out how to convert from Celsius to Kelvin, and it's quite straightforward. I'll also give you the formula for Rankins just so that you have it. All right, let's look at our equations quickly. We'll do a little bit of the math and then we'll break before the next video. So conversions between the temperature scales. Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8. Some of you will also know an equation. Instead of using 1.8, they will write it as 5/9 times Fahrenheit minus 32. I didn't have the formula written down in front of me. I had to think about it for a second. Okay, so that's another way you may see it written. Kelvins, is the easiest conversion. It's probably the favorite one to do. For Kelvin conversion, you take your degrees Celsius and we're going to add 273 to it. So it's just a linear conversion, but the one for Celsius to Fahrenheit is a little bit more involved. We have a 2-step problem in this case. I'm going to use Fahrenheit minus 32 divided by 1.8. I'm going to use this formula to do all the problems on this page. You're welcome to use the other formula if you would like. So let's begin with a question. We have 65 degrees Fahrenheit, and we want to know how many degrees Celsius is that equal to. So we're going to take our formula. Degrees Celsius is equal to 65 minus 32. Just put the 65 where the degrees Fahrenheit is divided by 1.8. Some people, for estimating purposes, will say 65 minus 32 divided by 32. That makes for some good mental math estimating if you find yourself in a scenario where you don't have to be super accurate, but you're wanting just to kind of get a ballpark figure. So you're going to take 65, subtract 32 first, and then divide by 1.8, and you will get degrees Celsius is equal to 16.5. This is a constant argument at our house. Is 65 degrees too cool? I definitely think it is, but I'm not sure I'm about to win that argument. Apparently, it's the ideal sleeping temperature. I'm not sure exactly how to get around that one. For B, -4 degrees Celsius is equal to how many degrees Fahrenheit? Well, in this case, we're going to put the -4 where our Celsius was. So -4 is equal to, we'll keep our Fahrenheit alone. So degrees Fahrenheit minus 32 divided by 1.8. Now, this is where sometimes people will make mistakes when they're doing some rearranging. So what we need to do, we'll pretend there's brackets around that because they're implied. Multiply both sides by 1.8. So -4 times 1.8 is going to leave us with, oops, -7.2 equal to Fahrenheit minus 32. Add 32 to both sides. Remember, we're always doing the opposite thing. Add 32 to both sides, and the degrees Fahrenheit is equal to 24.8 degrees. Okay. So 24.8 degrees Fahrenheit. Moving on to the next question, we have 24 degrees Celsius equals how many kelvins? So let's take our formula. Kelvins is just equal to the degrees Celsius plus 273. So 24 plus 273 leaves us with 297 kelvins. If I wanted to go from Fahrenheit to kelvins, first I have to go Celsius. Okay, so to get to Celsius, we're going to take our formula. Degrees Celsius is equal to 120 minus 32 divided by 1.8. And that leaves us with 48.9. Then to get to kelvins, that's equal to 48.9 plus 273, which gives us 321.9 kelvins. So relatively straightforward calculations to do. I'm going to assume if you're in the HVAC program, you're quite used to doing those conversions already. This was just probably a quick review for you. If you're in the wind turbine program, you're probably reasonably familiar with them, but I know you've got all the algebra background for doing them already. Let's look at the, oops, and that's where we're going to take a break.